Welcome to the video lecture of ICE Academy. Today we'll discuss a topic called as Laplace transform. Now when you talk about the gate prospect, the marks from this chapter directly in gate would be 0 to 2 marks. If you see the average of the last 10 years papers. Normally this is important for electronics students or electrical students when they study for control systems or other technical subjects, but as because it is in our syllabus of engineering mathematics, we'll have to just discuss what are Laplace and what are the effects of this Laplace and how to solve question based on Laplace. Now what one important thing, first of all, you have to understand why we are discussing Laplace. It is very essential for us to understand why we are discussing Laplace. We are discussing Laplace because sometimes the domain analysis in time, you know, there most of the things are in time domain, you know. So we are changing with respect to time, pressure, volume, whatever, we are changing with respect to time. But it is difficult. Some analysis are difficult to analyze. Sometimes, I'm not saying always, sometimes. For some analysis, right? For let's say for some analysis, this is difficult. So what we do is we convert this into frequency domain, where we can easily solve this particular thing. Time domain is basically represented by t and frequency domain is represented by s, and that can be done by Laplace transform. This can be done by Laplace transform. Clear? So basically Laplace transform converts time domain signals to frequency domain. Correct? We have got it very clearly, right? So basically Laplace transform's role is to convert time domain to frequency domain, right? Now what is the statement of Laplace transform? Let us discuss that. We'll say Laplace transform, basic definition of Laplace transform is given as, let ft be a function of time. This is in time domain. It is, let's stop. It is assumed that the value of the function ft is 0 for t less than 0. That means we are saying that the function do not exist when we are discussing. When we are saying for t less than 0, the function is not existing, right? And we also know that ft is continuous for all t's from 0 to infinity. Then the Laplace transform is given of ft is nothing but Laplace of ft. This is the Laplace operator, basically is equal to f of s, and mathematically it is represented by 0 to infinity e raised to minus st ft dt. Is very much important for this chapter, right? Where s is the complex frequency, where s is the complex frequency given by s is nothing but sigma plus j omega. Sigma is the real part and omega is the imaginary part, right? Now I want to couple of terms, like for example e raised to minus st is called as the kernel, not military one, kernel of the function, and L is the Laplace transform operator, what we call, right? So this is how it works. Now sometimes we can evaluate a two-sided function. This is basically for a single-sided function. Sometimes for a two-sided functions, the Laplace of ft can be also written as integration minus infinity to infinity. The two-sided function e raised to minus st into ft dt for a two-sided function. For a two-sided ft, so the both-sided ft. Clear? Similarly, if you talk about the inverse, so it is very simple. Inverse Laplace. Inverse Laplace is denoted only by L inverse. Now this will be converting the frequency domain to time domain. This is frequency domain to time domain, right? And if you want to convert this particular thing, is very simple. You can convert, right? Okay. Let us understand some basic formulas of Laplace. I'll give you the basic idea. Let's say I want the Laplace of ft is equals to 1. Ft is equals to 1. So what will be the Laplace of ft? Laplace of ft will become integration of 0 to infinity e raised to minus st into ft, that is 1. dt or ds? Dt. Right? So integration equal to e raised to minus st upon minus s. Limits are from 0 to infinity. It is 1 by minus s. I have taken separately. So it becomes 1 upon e raised to st. Limits is 0 to infinity. Now if I substitute the limit, e raised to infinity will become infinity, which is 0. This is nothing but minus 1 by s of 1 upon infinity minus 1 upon e raised to 0, which will be 1. So it is 1 by s. So we can directly remember this as a result that t in time domain, if I Laplace this, then it will become 1 by s. Clear? Not t, 1. 1 in time domain will be equal to 1 by s in frequency domain. Fine. Similarly, there can be many transformation, right? If you do it for t, in fact, e raised to minus st into t, if you solve it, it will be coming out to be 1 by s square. So I'll give you a list of Laplace transforms, some standard Laplace transform. What are the standard transforms? Let's say this is function, and I will write down the transform. Function is, let's say, impulse response del of t. Transform is 1. 1 we have just seen, 1 by s. If you say t, it is 1 by s square. T raised to n, it will become n factorial upon s raised to n plus 1. Now, to bifurcate these things very smoothly, then you can have sine omega t. Many functions you will find in sine omega t times, right, is omega upon s square plus omega square. Similarly, when you talk about cos omega t would be s upon s square plus omega square. Then e raised to at is nothing but 1 upon s minus a. Then if it is something like e raised to at into cos omega t, e raised to at into cos omega t, then this would be nothing but shifting. It will happen s minus a upon s minus a the whole square plus omega square. Similarly, if we do e raised to at into sine omega t, so this will be normally sine, what do you write? Omega. So we will keep omega upon s minus a the whole square plus omega square. This is how you can keep this particular thing, right? One important result is we will use gamma function here, t raised to 1 by 2, because for t raised to n, the n should be greater than or equal to 1. So this is directly, you can remember, it is under root of pi upon 2s to the power 3 by 2. You can prove it. We'll use through gamma functions. We can prove this particular thing also. So these are how we can calculate the Laplaces of different standard functions. Right? Now we'll solve a couple of problems so that we can understand how it works. Let's take this one question. Find the Laplace of, or the Laplace transform of. So Laplace transform, if you see, of s plus 9 into s square plus 6s plus 13, right? So first let us multiply this. This will become s cube plus 6s square plus 13s plus 9s square plus 9 6 is 54s plus 117, right? So you want Laplace transform inverse, sorry, not transform, this is inverse. Inverse also we can do it in the same fashion, right? If we know the Laplace, we can find out the inverse also, right? It is just the opposite of that particular thing. So if you simplify, this will become s cube plus it will become how much? 15s square plus 67s plus 117. This is basically the Laplace, right? Sorry, this is the problem is actually this is divided by, right? So I'm sorry, the problem is actually divided by. So what we will do is we'll find only the denominator factors. So otherwise I will not be able to solve it, because that's what I thought. Okay, how can this be solved? So you want the Laplace transform of fs, so that will be nothing but s plus 9 upon, the denominator can be written as s plus 3 the whole square plus 4, right? So we can say this is nothing but, can I say it is e raised to minus 3t. I can take out, and this is Laplace inverse of s plus 6 upon, so right, s plus 4. So this will become how much? Directly we can say now it is e raised to minus 3t. You can separate, right? You can separate this. You can say it is s upon s square plus 4 and plus 6 Laplace inverse of 6 upon s square plus 4. So one will convert to cos and one will convert to sine. It will become e raised to minus 3t into cos 2t. The first part is very simple. Plus 3 you can take common and you can say it is 3 sine 2t. Right? So this will become your Laplace inverse. Clear? So this is how we can actually solve the questions based on Laplace fundamental. Right?